let's talk about the mechanism of a chemical reaction. So if we consider this reaction where two molecules of NO react with oxygen to form two NO2s, this is a really common atmospheric reaction that happens when nitric oxide emissions from cars interact with oxygen in the atmosphere. We have found that the rate law for that reaction is NO squared times O2. So we're second order in NO and first order in O2. Now, while studying this reaction, we found that there exists N2O2 for a brief time in the reaction mixture. What does that mean? It must mean that on the molecular level, it is not that two molecules of NO collide with a single molecule of O2 to form two molecules of NO2 in a one-step process. So it's not that you have all three of those things that collide all at once and rearrange their bonds. Instead, it means that this reaction happens in more than one step. So let's instead propose that what actually happens in this reaction is that the two NO molecules collide with each other to make N2O2, and then N2O2 collides with an O2 molecule to make the two NO2s. The chemical equation at the bottom, the balanced chemical equation, it gives us the overall reaction, but it doesn't necessarily describe how the reaction occurs on the molecular level, what collisions actually happen. A reaction mechanism is a sequence of elementary steps of individual reactions that do describe the pathway from reactants to products. So the reactants are the starting point, the products are the destination, and then the mechanism is what shows us the pathway in between those two stops. An elementary step is a single step in a reaction mechanism. It does represent a molecular level collision. So we're imagining that it's actually two NOs that collide to make N2O2. N2O2 is thus an intermediate. It appears in the reaction mechanism, but not in the overall balanced equation, because it is produced in the first step and then consumed in the second step. So we can't necessarily use a microscope to look at the individual molecules while they're being formed. So instead, mechanisms are usually couched as being proposals, right? This is what we're imagining is happening in the reaction. And so mechanisms, proposed mechanisms, they have to follow some rules. First, the elementary steps have to add up to the overall stoichiometry, because the starting point and the ending point have to be the same. The rate law of the mechanism has to match the experimental rate law. We said before that you have to measure the rate law for an overall reaction with experiments, like the method of initial rates or using the integrated rate law. And so the mechanism that would be predicted for a particular mechanism, for that mechanism to be reasonable, it needs to match the experiment. The individual steps also need to be what we call chemically reasonable. And there's not a great way for you at this level to work out what chemically reasonable means. That's something you'll refine over time. But at the very least, it's reasonable for two molecules to collide, or maybe even three molecules, but it's not reasonable to require 6 molecules to simultaneously collide in exactly the right orientation for a reaction to happen. So for you, this is a lot related to the reaction order. So we can write the rate law of an elementary step using the coefficients as the molecularities. So for example, if your elementary step was reactant A goes to products, then the rate law for that step would be rate equals K times A to the first power. If your reaction was A plus B goes to products, then rate equals K times A to the first power and B to the second power. And if you had two A's colliding to make products, then that reaction would be second order in A. Now hold on. I told you before that you could not write the rate law based on the coefficients, and that is true for the overall reaction. However, since these are elementary steps, and we have said these are elementary steps, they represent molecular collisions, we can write the rate law. Because, for example, in the third reaction, since it is actually an A molecule colliding with another A molecule, the concentration dependence of the rate of that reaction is going to be proportional to the square of the concentration. So if you can write the rate law for an elementary step based on the coefficients, but not for the overall reaction. So how do you determine the rate law for an overall reaction? Remember, you use an experiment, something like method of initial rates or the integrated rate law. So let's practice. The rate law for an elementary reaction follows from its molecularity because an elementary reaction is an individual molecular event. So let's write the rate laws for these reactions and label them as unimolecular, bimolecular, or termolecular. So in this first one, we're going to have that the rate law equals rate times K times the concentration of the reactants, which here is CH3CN acetonitrile. And that'll be raised to the first power because the reactant has a 1 for a coefficient. This is a unimolecular step because the overall exponents on the concentration is just 1. We have one molecule, unimolecular, reacting in this molecular event. For the second one, we have that rate equals K times ozone, O3, times NO, both of those to the first power. And this is a bimolecular elementary step because two molecules are colliding. And it could be two of the same molecules or two different molecules. In the last one, we have rate equals, and we see we have two Cl's, so that'll be Cl squared times N2. And this is what we would call a termolecular step. Ter is for 3, because 3 molecules, 3 atoms, are combining in order to make the products of that step. So determine the rate law for an overall mechanism in order to compare it to the experimental rate law. We write the rate law based on the slowest step. The slowest step, also called the rate determining step. The slowest step is what determines how fast the reaction can go overall. So for this proposed mechanism, we would write the rate law based on the slowest step, which here is the first step. So the rate law will be that rate equals K times NO squared times H2. And so the steps that happen after the first step, they do not affect the rate after the slow step. So that's the rate law for this mechanism, and now we could get some experimental data and see if this mechanism could be a reasonable fit compared to our experiments. It gets a little more tricky if the first step isn't the slow step. And so let's do an example of that. In this case, we see that the second step is the slow step. So here, we'll still start by writing the rate law based on the second step. And I'm going to call the rate constant of this second step, I'm going to call it K2. So the rate equals K2 times N2O2 times O2. So we can't stop there because we have an intermediate in our rate law. And so we don't want an intermediate in our rate law because we can't control the concentration of an intermediate when we set up our experiments. We want to compare our experiments to the reactants because, like, if you imagine we're in the lab and we're making solutions, the reactant concentrations are the things that we can control and measure. So we need to replace this N2O2. We're going to use the first step to do that. We see that this first step has double arrows, showing that this reaction can go both forward, K1, and backwards, K-1. And we're going to write the rate, so we know that, or we're going to define that, when this step is in equilibrium, that the rate of the forward reaction is going to equal the rate of the reverse reaction for step 1. Okay, and so we can write the rate law of the forward reaction, which is going to be K1 times NO squared, and that's going to equal the rate law of the reverse reaction, K-1 times N2O2. So now we have an equation that relates the intermediate concentration to the reactant concentration. So we can rearrange this to solve for N2O2. So that will be N2O2 equals K1 divided by K negative 1 times NO squared. Okay, now we have an expression for N2O2 in terms of the reactants. We can put this piece back into our rate law to substitute for the N2O2. So that'll be K2, and then we're going to put this whole thing in K1 divided by K negative 1 times NO squared times O2. And if we simplify this a little bit, we're going to say, so this is K1, K2 divided by K negative 1 times NO squared times O2. When we do an experiment, we don't get all of these individual rate constants. Instead, we just measure a K observed. So we're going to say is K observed times NO squared times O2, where K observed equals K1 times K2 divided by K negative 1. So here is the rate law for our mechanism, and we can compare that to the experimental rate law, which we were given here in the problem, and we can see that, look, K times NO squared times O2, that is the same rate law that we observe experimentally. So this mechanism is reasonable for this overall reaction.